All right, so we were saying the Z transform, which is the discrete time counterpart of the real part expanded version of Fourier transform. In continuous time, we had the Laplace transform, and in discrete time, we have the Z transform. Now, we have seen region of convergence, we have seen poles, but I think I have forgotten to mention about one thing regarding the overall pole zero approach, which is more related to the zeros this time, because we have seen the poles, but we haven't seen the zeros. I want you to focus back to this only example that we have seen, the Z transform. In this Z transform, we can see that when Z is equal to A, the denominator becomes 1 minus 1, which is 0, and that makes a pole. But is there a 0 is a question. So do we have a 0 here? And the answer is actually yes, there is 1 0, and that happens when Z is equal to 0. When Z is equal to 0, Z inverse becomes infinity, so the denominator becomes plus or minus infinity. It doesn't really matter, but when you divide 1 by plus or minus infinity, that makes 0. But it's difficult to see it that way, so instead of that, you may want to convert this into a totally new form. It's not a totally new form, just multiply the numerator and the denominator by Z, and you see that this is equal to actually Z over Z minus A. It's the same. I multiplied both the numerator and the denominator by Z, and this is what I get. And from here, I can see that Z is equal to 0 is a 0 because Z is in the numerator, and it becomes 0 when it becomes 0. And when Z is equal to A, then the denominator becomes 0, which makes a pole. Okay, be careful about the zeros too. So it will be wise for us to also put a 0 in the center like this, which is the correct way of making the representation. In fact, this one is also equal to Z over Z minus A. We can also write it that way. It's the same. Now let's give another example. Let's continue with another example that contains two first-order systems. That's very regular practice. Consisting of two exponentials. So x of n for this example is equal to, let's say, 7 times 1 over 3 to the power n u of n minus 6 times 1 over 2 to the power n u of n. So we have two exponential terms, and they seem to be decaying exponentials. So we also have the Fourier transform of this signal x of n. 1 over 3 to the power n is a decaying exponential for positive side, and because of this u of n, it is on the positive side, so it's a decaying exponential. 1 over 2 to the power n is also a decaying exponential. So what are the Z transforms of these things? It's easy. Individually, we can take the Z transforms of each terms, and then using the linearity property of the Z transform, we can just combine them, add them up. So for the first part, it is 1 over 1 minus 1 over 3 Z inverse, like A Z inverse, minus 6 times 1 over 1 minus 1 over 2 Z inverse. Okay. And the rest is just algebra. You have to make the necessary simplifications and all that. It is wise to multiply the numerator by Z at both parts and then make the simplification. That may help, but I'm not going to do the steps. I'm just going to give you the eventual overall simplified form. And the simplified form is in the form of Z in the numerator as well, which will help me to see the zeros too. So in the simplified form, this is the numerator part, z times z minus 3 over 2, which means there are two zeros. One of them is z is equal to 0. The other one is z is equal to 3 over 2. So those two are the zeros. And in the denominator, we have these two terms. It's obvious. The denominator is quite obvious because I can see that one pole is at 1 over 3, the other pole is at 1 over 2. So z minus 1 over 3 and z minus 1 over 2 must appear anyway, right? So it's quite an obvious denominator. The denominator, there's no confusion about that. Now, how about the region of convergence? What can we say about it, and how do we notate the region of convergence? There are two poles and two zeros. Let's try to draw them. Let's try to see where they are. One of the poles is at 1 over 3. Let's say it's here, okay, 1 over 3. Then there is another pole at 1 over 2. Okay, these two are the poles. And there is a 0 at z is equal to 0, and there is another 0 at 3 over 2, which is 1.5. So it must be a little bit far away. Sorry about this. This is 1.5 is maybe somewhere here. This is 3 over 2. As you see on the real axis, it's a little bit far away, but it's just a 0. It doesn't really affect the region of convergence circle. So it can be anywhere. But we need to show it. So it's a right-hand sided signal. Therefore, the region of convergence is to the out of the circles. It's to the out of a circle with a radius of 1 over 3 for the first part, and it is to the out of 1 over 2 for the second part. And what is the overall region of convergence? It's the intersection of these two, which is the outside of the larger circle, which is 1 over 2. So the region of convergence is like this region, out of the circle with a radius of 1 over 2. We can write it as a continuation of the result, as magnitude of z is greater than 1 over 2. This is the region of convergence. So we have found the z transform, and that gives us the complete answer. But we can talk a little bit on it. For example, z is greater than 1 over 2 in magnitude means out of this circle, and that out of that circle also includes the unit circle, a circle with a radius of 1, which is the necessary condition for the existence of the Fourier transform. So the Fourier transform of this signal actually exists. Or if this x of n is not x of n, but it is h of n, which is the impulse response of a discrete time filter, since the Fourier transform exists and since the region of convergence includes the unit circle, what we are going to say about the system is that the system with this impulse response is a stable system. So just like when j omega axis is included in the region of convergence for the Laplace transform, we say that the system is stable. We say that the system is stable again, even though it's a discrete time system. All right, let's continue. Now another example. And in this new example, we will see that the poles and the zeros need not be only on the real axis. Sometimes they deviate, but as long as the signal itself is a real valued signal, we will see that the poles and the zeros will appear in reciprocal pairs. Like if it is to the upside on the imaginary axis, for a certain value of j omega, then minus j omega value must also appear down there. So they come in conjugate pairs. And in this example, we will see that x of n is equal to 1 over 3 to the power n times sine pi over 4 n u of n. Okay, so how can we really find the Z transform of this one, and how can we relate it to something already in an exponential form? And you must immediately recognize that if you have a sinusoid like this, it can be a sine, a cosine, there can be a phase factor added to the angle, but regardless of what, it is also available in an exponential form using the Euler's expansion, right? So let's do the Euler's expansion, and we see that this thing becomes equal to 1/3 to the power n, which is already in the exponential form, times 1/2j. What's happening? I don't know. 1/2j times e to the j pi over 4n minus e to the minus j pi over 4n. Now, you may think that one of them is 1/3 to the power n, the other one is e to the n, or e to the j pi over 4n, but e to the j pi over 4 itself is just a number. It's like a. So e to the j pi over 4n is actually meaning that it is to the power n of a number which is e to the j pi over 4, which is just a complex number. Its value is a. So these terms share the common concept of something to the power n. And as long as we have something to the power n times u of n, of course, there's a u of n at the end. If there's no u of n at the end, things are different. We will come back to that. Therefore, we have essentially two exponential terms, two separate exponential terms. One of them is 1/3 times e to the j pi over 4 to the power n. This is one term. And the other term is, of course, there's a 1/2j as well. Let's say 2j times 3, which makes 6j, but it doesn't really matter. 2j times 3. Excuse me, 2j is not there. I will have to erase. I'm sorry about this mistake that I make. It's really 1/3 only. And this one is also 1/3. The 1/2j thing is here. It's not inside the exponent term. Excuse me about that. 1/3 e to the minus j pi over 4. Yeah, this is correct. To the power n times u of n. Sorry. So this is the overall thing. And in this overall thing, we have two terms, as you see. And those two terms can be easily proceeded to the Z transform. The Z transform is equal to x of z is equal to 1/2j in parentheses 1/1 minus 1/3 e to the j pi over 4 z inverse minus 1/1 minus 1/3 e to the minus j pi over 4 z inverse. Z inverse. This expression. This is the expression. So we have two poles. One of the poles is at 1/3 e to the j pi over 4. It's a value, it's a number, complex number. The other one is at 1/3 e to the minus j pi over 4, another number. Now, these two numbers are conjugates of one another. And if you just leave it like this without any further simplification or anything, you should be, an engineering student in electrical engineering should be able to locate them on the axis and at least tell me where the zeros, where the poles are. The zeros, well, the zeros are at z is equal to 0, clearly, because when z is equal to 0, the denominators of the two terms diverge to infinity, and 1 over infinity will become 0. But how can we locate the poles is more important. And can you tell me what is the region of convergence just by locating these poles? So the region of convergence is, first of all, magnitude of z is greater than something. Why? Because there is a u of n. It's a right-hand sided signal. So the region of convergence is out of a circle. The magnitude of z is radius, and radius is greater than some value. What is that value? Can you see it? If you can see it, I will keep an eye on the chat screen so that you can tell me the result. But meanwhile, I will continue with the discussion. This is the real, this is the imaginary axis. And one of them is at 1 over 3 e to the j pi over 4. Where is 1 over 3 e to the j pi over 4? If you are an unknowing student or an engineer who doesn't know much about mathematics, you may try to replace e to the j pi over 4 by 1 over 2 cosine pi over 4 plus j sine pi over 4. You may want to do that. And pi over 4 is a known angle, by the way. It's 45 degrees. So cosine of that, 1 over square root of 2 terms. You may remember the cosines and sines. So you will be able to determine what the value of e to the j pi over 4 is. But if you are a smart, a clever engineer or a student thereof, then you will actually think like this. There is a 1 over 3, which shows us the magnitude. And e to the j pi over 4, that pi over 4 is the angle. So actually we have a situation like this. This is point 1 over 3, okay? And at an angle of 45 degrees or pi over 4 radians, we make plus 45 degrees rotation and we locate the pole. So this length is essentially 1 over 3. Okay, the radius, the magnitude of that pole, the distance from the origin to the pole position is 1 over 3. And we have this pole. Let me mark the pole with the red so that it does not get confused with other colors. If it is 1 over 3 j pi over 4, it is there. I draw a radius of 1 over 3 and rotate it by an amount of pi over 4. That's where it is, okay? Be smart and try to understand this. Similarly, a negative 45 degrees rotated version, because it's a e to the minus j pi over 4 minus pi over 4 degrees rotated version of the same magnitude. So we have this length also to be equal to 1 over 3, and we have a pole over there. We have, these are the two poles, and these two poles are conjugates of one another. Okay? They are conjugate pairs. One of them is rotated by minus 45 degrees, the other one is rotated by plus 45 degrees. So these two. And they are there, so they are the poles. But what is the radius then? The radius is already 1 over 3. We draw a circle of radius 1 over 3, and out of this radius makes the region of convergence, which means magnitude of z is greater than 1 over 3. That's it. Do you understand this? Is there a question about that? In fact, immediately when I see this z transform, I understand that essentially 1 over 3 is the magnitude of the pole, the radius of the pole. The other is just an angle, because when you take the absolute value, the magnitude of this exponential part, it will give me 1. So this is the critical radius length. Same for this one, same for this one. There are two poles, but both of them are with the same radius. Now, even before that, let me be honest about it. When I see the question here, I can also say that the region of convergence is magnitude of z greater than 1/3, because this sinusoid is oscillating between minus and +1. So magnitude-wise, it affects nothing. The radius is only determined by a real exponential, and that makes the radius which I must exceed. So magnitude of z, that's the radius, is greater than 1/3. Even from the question, without solving this question, if this were a test question, which is very likely in such distance learning applications, your questions may perfectly be test questions or fill in the blanks or many of them. And when you see this kind of a question, which of the below is the correct region of convergence, may be a test question, and when I see it, I just choose the appropriate selection of magnitude of z is greater than 1/3. That's it, without any confusion with this sinusoid or anything. Okay, be careful about that. All right, now is a little bit different example, which teaches us a lot of things. And it teaches us a lot of things regarding the Laplace transform similarity too. The question is as follows. Suppose that x of n is equal to what is this? A to the n between, oh my God, between 0 and let's say n minus 1. N minus 1. So it's a finite support signal with some values, a to the n, some finite values. And the values are not infinity, and it's equal to 0 0 else. Okay, so it's a finite signal. Now, if you may remember from the Laplace transform that if you have a finite signal, the region of convergence was the entire S-plane. It happens to be the entire S-plane. So the answer is, again, we will have a Z transform, but the region of convergence is expected to be the entire Z-plane. Is it going to be like that? It must be like that. Let us see. So first, let's find the Z transform. What? Oh my goodness. X of Z is equal to summation. I'm just using the formula here. And the summation run is from 0 to n minus 1, because x of n is already there. Out of this domain, x of n is 0, so I don't need to sum all the way from minus infinity to plus infinity. Most of the terms will be just zeros. A to the n, z to the minus n. Z to the minus n. Okay, so this is the Z transform, and there may be some poles and some zeros. And when you do this summation, it's a finite power series sum. It's not a power series, it's a series sum, but it's a finite one from 0 to something. So you may know the way to do it. You can combine a times z to the minus 1 as together and say that it's equal to b. What is the summation b to the n for n is equal to 0 to n capital N minus 1? We know the formula. Okay, it is 1 minus this to the power n divided by 1 minus this, kind of a formula. You may remember the finite series sum. Now I'm going to use it and then simplify the formula to this. 1 over z to the power n minus 1, or z to the power minus n plus 1. You can write it like this. Z to the n minus a to the n over z minus a. This is a grossly simplified expression, but it's the final form, okay? And when we look at the final form here, we start observing that there are risks of obtaining some poles. Of course, I can see a lot of zeros too. But where are the zeros and where are the poles, or what is a pole? Let's try. Let's try to draw them. The real and the imaginary parts are here. First of all, I can see that there is capital N minus 1 poles at a single point, which is at z is equal to 0. So we have multiples of poles here. It's full of poles if you focus to z is equal to 0. Now, z is equal to 0 point is not included in the z plane or the complex plane. That's interesting. You may say that, well, it's perfectly within the plane. It's in the center of it. So why do we say that it's not in the z plane or the complex plane? It's because z is equal to 0 corresponds to an infinity point. Like, for example, z is equal to infinity. If I say it like this, z is equal to infinity, will you be able to draw it on this finite z plane? No, it's out of it, we say. Just like that, z is equal to 0 is also a point corresponding to sigma is equal to minus infinity. So sigma is equal to minus infinity, in a sense, from logic, or 0 radius, essentially corresponds to an infinite point. So z is equal to 0 for the z transform is an infinite point. So these poles actually do not disturb the fact that if these are the only poles that we have, then the region of convergence is the entire z-plane, except z is equal to 0, of course, but z is equal to 0 is an infinity point. So we say the entire z-plane is the region of convergence if these are the only poles. But we seem to have another pole here, and that is when z is equal to a. So let's also plot it. Z is equal to a. This is a pole. But then again, we take a look at the numerator and start seeing that we have several zeros too. And one of the zeros is at z is equal to a too, because when z is equal to a, z to the n minus a to the n will also become 0. Therefore, that pole and 0 will cancel one another. We have a 0 here too. Maybe I should write it or draw it in a different color, like red colors, let's say. There's a 0 here. And you may further say that, in fact, at z is equal to a, we have multiple zeros, right? It looks like that. Z to the n minus a to the n is equal to 0 is the equation. So from here, we say z to the n minus a to the n is equal to 0. These are the 0 points, which makes z to the n is equal to a to the n. So we have n solutions at z is equal to a. You are wrong. Think of it like this. I will open a box here. Think of it like this. If I say z square is equal to 2 square, okay? So what are the solutions of z? Z is equal to, type it. I'm expecting from the chat an answer. Z is equal to plus and minus 2. Yes, a few students already indicate that the solutions are plus and minus 2. Good. So we have two different solutions. What I'm going to say is that z to the n is equal to a to the n also has n different solutions, and one of them is z is equal to a. Like z is equal to 2 is one of the solutions. The other one is minus 2. How about this one? Z to the 4 is equal to 2 to the 4. What are the solutions that you may propose to this? Again, I may expect some answers from the chat. Let me open the chat window to see myself what you are saying. What are the solutions to z to the 4 is equal to 2 to the 4? Same. Plus and minus 2 is one candidate answer. That's a plausible, reasonable answer. Any other answers? Because in fact, it's not the same. We must have 4 solutions. Yes. Plus and minus 2 as well as plus and minus 2j. Yeah, right? So how do we get those 4 solutions? Z can be 2 minus 2, 2j, and minus 2j. How do we obtain this? Or if I extend the question further to z to the 6 is equal to 2 to the 6, then what will be your answers for the solution? How are you going to indicate the answer? It's simple, and it requires only a little bit knowledge of complex calculus. Like this, we have the complex plane like this, and z to the 6 is equal to 2 to the 6, or z to the 4 is equal to 2 to the 4 means that z is equal to 2 is the radius. Okay, so we draw a circle with a radius of 2. Let's think of only z to the 4 is equal to 2 to the 4. So this 2 pi circle is divided into 4 equal angles. We divide it to 4 angles. The first angle is itself. Then this is the other solution. If you divide equally into 4, this is the other solution, and this is the other solution. And the first solution is 2. The other one is 2j. The other one is minus 2. The other one is minus 2j. This is how you find the answer to z to the n is equal to a to the n. You say that it's actually z to the n is equal to 2 to the n plus 2 pi j, or something like that. And that 2 pi j is also further divided into n angles. So we just equally divide into n angles. For example, if the question was z to the 6 is equal to 2 to the 6, the answers would be, it may be difficult to express these numbers analytically, but graphically I can show what they are. Then I divide this 2 pi circle into 6 angles, equal angles. One of them is itself, okay? Then the others will be at, one of them will be at 60 degrees, because 360 divided by 6 is 60 degrees. So each one is separated by 60 degrees. The other one is 180 degrees, 120 degrees, sorry. The other one is at 180 degrees. The other one is at here, which is 240, I guess, whatever. The other one is here. So as you see, I am splitting this 2 pi circle into 6 parts. I'm dividing it into 6 parts. And this is the first solution. This is the second solution. This is the third, fourth, fifth, and the sixth solutions. You can convert these things into complex numbers. You can express them using the Euler's formula, using cosines and sines if you wish. Of course, they will be complicated, but they are there. Now, coming back to z to the n minus a to the n is equal to 0 solution. So z to the n is equal to a to the n. What we really need to do is we have to divide this circle, 2 pi circle, into capital N equal angles, depending on the value of capital N, of course. But they will be all along the circle, like this. And let's say that, for example, we must give some numerical values to this capital N. Let's say capital N is equal to 8. Okay, for capital N is equal to, sorry, excuse me. Let's say capital N is equal to 8. Then the zeros, the solution to z to the n is equal to a to the n will be at 45 degrees, 90 degrees, here, 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 and here. And one of them will be at z is equal to a, the one that cancels the pole at z is equal to a. The others are the other zeros, okay? So the pole zero pattern essentially looks like this. And this pole and zero are canceled. Pole and zero cancellation. Therefore, we don't have a pole at z is equal to a. All the poles are at z is equal to 0, which are not on the finite z plane. They are assumed to be not on the finite z plane. Therefore, it's to the out of 0 point, which includes the whole z plane. So we write region of convergence is the z plane, or the entire z plane, all of it. That's why we don't really come up with a limit. Just like the Laplace case, there's a pole zero cancellation that we have. Be careful about these pole zero cancellations. They are very critical. Okay, another example. And this new example, x of n, is this time a two-sided signal. So for n positive or negative, it's like this. And if b is less than 1 in magnitude, by the way, it will make decaying exponentials to both sides. And let's assume that b is positive. Okay. So what is the z transform of it? For this, we have to split this expression into two parts. One of them is b to the n u of n. U of n. And the other part is b to the minus n u of minus n minus 1. As you see, it's a little bit dirtier looking than the Laplace transform, because u of t and u of minus t are just opposites of one another, whereas u of n's complementary signal is u of minus n minus 1. There's a minus 1 further. If you say u of minus n only, since u of n will be 1 at 0 and u of minus n will also be 1 at 0, they will merge together at 0, which would make an incorrect solution. So this is x of n, and x of z is the z transform of these two terms. And the first one is easy. I'm tired of this. It's 1 over 1 minus bz inverse. If only I could write properly. 1 minus bz to the minus 1. Let me write slowly. Minus, the minus comes from the left-hand sided part. 1 over 1 minus b inverse z inverse. That is the z transform of the negative sided term. Now, what is the region of convergence? We can you may try to combine these two expressions and simplify it a little bit, but that's not the point here now. I'm more interested in the regions of convergences. First of all, we have two poles appearing. One of them is at z is equal to b, okay, and the other one is at z is equal to 1 over b, or b inverse. These are the two poles. For this one, it corresponds to the right-hand side of the signal, so the region of convergence is to the out of the circle with a radius b, to the out of b, And for this one, it corresponds to a left-hand side of the signal. Therefore, it's to the inside of 1 over b. So I should better have b to be somewhere here, for example. Maybe 1 is here, so b is less than 1. That would make 1 over b greater than 1, like this. Then things are okay, because this is the radius with a b, and out of it is the region of convergence. For the first part, let me draw it. And then we have a 1 over b radius, like this. And it's to the inside of this 1 over b, which will be this disk. Okay, and the intersection of the two would correspond to the actual region of convergence, which is this disk. So that disk is the one that we need to write as the region of convergence, which can be simplified as the radius magnitude of z is greater than b and less than 1 over b. So this is the region of convergence expression that you have to write. And it, as you see, it works as long as b is less than 1 and 1 over b is therefore greater than 1. So let's look at the signal again. The signal is b to the magnitude of n. So if it is decaying to both sides, which means b is less than 1 in magnitude, that's fine. We have the region of convergence for a finite region. But if b is larger than 1 in magnitude, it may be like -2 or +5 or whatever, then it would be growing exponential to both sides, which is impossible to handle in Z transform. Therefore, if b is greater than 1, then the region of convergence would be empty set. So this is valid if b is less than 1 in magnitude, and its region of convergence would be an empty set if b is greater than 1 in magnitude. Okay. And interestingly, if b is less than 1, then I can see that this unit circle that I'm drawing as a solid circle this time, this one, is included in the region of convergence. So if the Z transform exists, the Fourier transform also exists. Or if this is the impulse response of a system, then it means that the system is stable automatically. Okay, now let's continue. This example is quite well understood. It's a very typical example, I guess. There is an inverse Z transform, of course. And the problems of the inverse Laplace transform is also available for the inverse Z transform, which is telling us that it's a complicated way of looking at things. The inverse Z transform would be like this. If you have the unit circle inside your region of convergence, if that is available to you, then choose r is equal to 1 and integrate over the unit circle. Take this integral, okay? It's a contour integral, it's a complex integral, which is the definition of the inverse Fourier transform, okay? That's a place where you can take the integral, r is equal to 1, which means don't take the inverse Z transform, but take the inverse Fourier transform. But if the unit circle is not included in the region of convergence, you cannot do that. Then you may have to choose another radius r and take this integral instead. But what is the definition of that integral? And the definition I will write, but is it a feasible integral? Will you be able to do that? It's another question. And it comes from here. X of z is equal to capital X of r times e to the j omega. That is the inverse Fourier transform of not excuse me, not inverse, the Fourier transform of not x of n, but x of n times r to the minus n, because of this r appearing here. R to the minus n times x of n. Okay, so this is the Fourier transform that is necessary to determine x of z for a certain r. And that gives me the equation that x of n times r to the minus n, which is the inside term of that Fourier transform expression, is therefore the inverse Fourier transform of x of z, capital X of r times e to the j omega n, which is x of z actually. Okay. And then from here we will construct our inverse z transform expression. Don't fear from this, okay? Don't be afraid, because you're literally not responsible for this kind of an expression or the evaluation of that. But I'm just showing you just to keep it complete. So x of n is equal to, therefore, r to the n times the inverse Fourier transform, which is 1 over 2 pi, come on, 1 over 2 pi integral in 2 pi x of r times e to the j omega n times e to the j omega n d omega. This is the definition of the inverse Fourier transform. So I'm just using it that way. Very well. Now I will collect some terms. I will write it like 1 over 2 pi, the integral over 2 pi x of r times e to the j omega n, and out of it there is an r to the n and e to the j omega n, which means r times e to the j omega n, j omega to the power n times d omega. Now a change of variables can be done. I can say that r times e to the j omega, if only it is omega, is equal to z. But I need something else. I need to find what is d omega with respect to dz, because one of them is in the exponent, the other one is here. I will replace every r times e to the j omega term. Why am I putting n here? These n's are erroneous. Excuse me about this. Yeah, more like this one. This is correct. Every time I see r times e to the j omega, I will say z. But how can I replace d omega? What kind of a dz will I replace? For that, I will have to take the derivative of both sides of r times e to the j omega is equal to z, and say it like this. dz is equal to j times r times e to the j omega d omega. Okay, we can write it like this. If you take the partial derivatives of both sides of this equation, this is what you will get. Now, this is the right-hand side of this one is this r times e to the j omega is z. Therefore, dz is j times z times d omega, which means d omega is equal to 1 over j times z inverse, or 1 over jz, if you like to say it as jz. 1 over j times z inverse is d omega times dz, of course. Okay. Now let's make all these substitutions. There's a 1 over 2 pi, and there is a 1 over j coming from here too, so I will include that one if I can, or 2 pi j, and an integral. Wow, it's getting worse. 1 over j. No, I'm not happy with this integral too. Yeah, at long last, an integral symbol. X of z, because x of r times e to the j omega is like that. And then r times e to the j omega to the power n is z to the n, z to the n, and then z to the minus 1, both of them. Now I will erase these all together and put it as z, write it as, sorry, z to the n minus 1, because there was a z to the n and there was a z to the minus 1, dz. So that's it. This is the inverse z transform, x of n. Let's put it in a box. I hope you like it. I don't, because there is also another ambiguity regarding the integral limits. Previously for omega, it was a duration of 2 pi. So omega from 0 to 2 pi, or omega from minus pi to pi, such a duration of 2 pi for omega. But how about z? Then what are the values of z? You can write it in 2 alternative ways. So the integral symbol could be written as r times e to the j0 to r times e to the j2 pi, or something like this, if you wish. Which is one notation. What is this r? What is the r here? R is any value within the region of convergence that is suitable for you. You can either write it like this or put this notation, which means a circular contour integral that I was describing at the top here. This contour integral over this r that you integrate. You choose an r and you vary omega from 0 to 2 pi. You trace it like that, or you start from minus pi and trace it all the way back to pi and things like that. Now, this is, as I say, just a definition. And I don't expect you to utilize it for finding the inverse Z transforms. So how will you find the inverse Z transforms? There are the classical way of finding the inverse Z transform is to put it into first order forms if you can, like the Laplace transform. And then from the first order systems, together with the region of convergences, you will take a look at the table, what it corresponds to. And from the table, you say that this part corresponds to this signal and this part corresponds to that signal, and you combine them. That's how you will find the inverse Z transform. There is also another Z transform discovery mode, which is trying to obtain a Z polynomial only in the form of a numerator. And every coefficient of that Z polynomial coefficient will correspond to the value of the signal, because we know that a time signal and its Z representation is just the signal and a polynomial which has these coefficients in the form of a Z polynomial, right? We know it. So that's how we are going to do that. We will continue with examples. It's a little bit late already. Let's meet again at 15:10. Okay. Until then, let's give some break and see you afterwards.